Here we are at Chapter 5. You may hear me sipping on my coffee from time to time. I'm going to be narrating this for you. Hopefully you're learning something. Let's get started. Using structs to structure related data. A struct or structure is a custom data type that lets you name and package together multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with a struct's data. Structs and enums, discussed in Chapter 6, are the building blocks for creating types in your program's domain to take full advantage of Rust compile time. Type checking. 5.1 of 5.3, defining an instantiating structs. Well, I'm sure you're going to see that I'm going to make some errors from time to time in my pronunciation. Hopefully you're just reading along with me. That's where you'll probably get the most out of this. Here we go. Structs are similar to tuples, which were discussed in Chapter 3. Like tuples, the pieces of a struct can be different types. Unlike with tuples, you'll name each piece of data so it's clear what the values mean. As a result of these names, structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the piece of data being grouped together. Then inside curly brackets, we define the names and types of the pieces of data, which we call fields. For example, listing 5-1 shows a struct that stores information about a user's account. Listing 5-1, a user struct definition. To use a struct after we've defined it, we create an instance of the struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct, and the added curly brackets contain pairs where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declare them in a struct. In other words, the struct definition is like a general template for the type. And instances fill in the template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5-2. Listing 5-2, creating an instance of the user struct. To get a specific value from a struct, we can use dot notation. If we wanted just the user's email address, we could use user1.email wherever we wanted to use this variable. If the instance is mutable, we can change the value by using the dot notation and assigning it to a particular field. Listing 5-3 shows how to change the value in the email field for a multiple user instance. Listing 5-3, changing the value of the email field of a user instance. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in the body function body to implicitly return that new instance. Listing 5.4 shows a build underscore user function that returns a user instance with a given email and username. The active field gets the value of true, and the sign underscore in underscore count gets a value of 1. Listing 5-4, a build underscore user function that takes an email and username and returns a user instance. To make sense to name the function parameters. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and usernames field names and variables is a bit tedious. If the struct has more fields, repeating each name would get even more annoying. Luckily, there is a convenient shorthand. Using the field NIT initial shorthand when variables and fields have the same name. Because the parameter names and the struct field names are exactly the same in listing 5-4, we can use the field initial shorthand syntax to rewrite builder underscore user so that it behaves exactly the same but doesn't have the repetition of email and username as shown in listing 5-5. Listing 5-5, a build underscore user function that uses field initial shorthand because the email and username parameters have the same name as struct fields. Here we are creating a new instance of the user struct, which has a field named email. We want to set the email's field value to the value in the email parameter of the build underscore user function. Because the email field and the email parameter have the same name, we only need to write email rather than email::email. Creating instances from other instances was struct update syntax. It's often useful to create a new instance of a struct that uses most of an old instance values but changes some. You'll do this using struct update syntax. First, listing 5-6 shows how we can create a new user instance in user2 without the updated syntax. We set new values for email and username, but otherwise use the same values from user1 that we created in the listing 5-2. Listing 5-6, creating a new user instance using some of the values from user1. Using struct update syntax, we can achieve the same effect with less code. As shown in listing 5-7, the syntax ... specifies the remaining fields not explicitly set should have the same value as the fields in the given instance. Listing 5-7, using struct update syntax to set new email and username values for a user instance, but use the rest of the values from the fields of the instance in the user1 variable. The code in listing 5-7 also creates an instance in the user2 that has a different value for email and username, but has the same values for the active and sign _in _count fields from user1. Using tuple structs without name fields to create different types. You can also define structs that look similar to tuples, called tuple structs. Tuple structs have the added meaning the struct name provides, but don't have the names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple be a different type from other tuples. The naming each field, as in a regular struct, would be verbose or redundant. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here are the definitions and usage of two tuple structs named color and point. Note the black and origin values are different types because they're instances of different tuple structs. Each struct you define each struct you define is its own type, even though the fields within the struct have the same types. For example, a function that takes a parameter of a color cannot take a point as an argument, even though both types are made up of three I32 values. Otherwise, tuple struct instances behave like tuples. You can deconstruct them into their individual pieces. You can use a dot followed by the index to access an individual value, and so on. Unit like structs without any fields. You can also define structs that don't have any fields. These are called unit-like structs because they behave similarly to the colons, the unit type. Unit-like structs can be useful in situations in which you need to implement a trait on some type but don't have any data that you want to store in the type itself. We'll discuss traits in Chapter 10. Ownership of struct data. In the user struct definition in listing 5-1, we used the owned string type rather than the and str string slice type. This is a deliberate choice because we want instances of this struct to own all of its data and for the data to be valid for as long as the entire struct is valid. It's possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in Chapter 10. Lifetimes ensure that the data referenced by the struct is valid for as long as the struct is. Let's say you want to store a reference in a struct without specifying lifetimes, like this, which won't work. In Chapter 10, we'll discuss how to fix these errors so you can store references in structs. But for now, we'll fix errors like these using owned types like string instead of references like and str. An example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start with single variables and then refactor the program until we're using structs instead. Let's make a new binary project with cargo called rectangles that we will take the width and the height of rectangle specified in pixels and calculate the area of the rectangle. Listing 5-8 shows a short program with one way of doing exactly that in our projects src/main.rs. Listing 5-8 calculating the area of a rectangle specified by separate width and height variables. Now run this program like cargo run. The area of the rectangle is 1500 square pixels. Even though listing 5-8 works and figures out the area of the rectangle by calling the area function with each dimension, we can do better. The width and the height are related to each other because together they describe one rectangle. The issue with this code is evident in the signature of area. The area function is supposed to calculate the area of the rectangle, but the function we wrote has two parameters. The parameters are related, but that's not expressed anywhere in our program. It would be more readable and more manageable to group width and heights together. We've already discussed one way we might do that in the tuple type section of chapter 3 by using tuples. Refactoring with tuples. Listing 5-9 shows another version of our program that uses tuples. Listing 5-9 specifying the width and height of the rectangle with tuples. In one way, this program is better. Tuples let us add a bit of structure, and we're now passing it just one argument. But in another way, this version is clear. Tuples don't name their elements, so our calculation has become more confusing because we have to index into the parts of the tuple. It doesn't matter if we've mixed up width and height for the area calculation, but if we want to draw the rectangle on the screen, it would matter. We would have to keep that in mind, that width is the tuple index 0 and height is the tuple index 1. If someone else worked on this code, they would have to figure this out. And keep in mind as well, it would be easy to forget or mix up these values and cause errors because we haven't conveyed the meaning of our data in the code. Refactoring with structs, adding more meaning. We use structs to add meaning by labeling the data. We can transform the tuple we're using into a data type with a name for the whole as well as names for the parts, as shown in listing 5-10. Listing 5-10, defining a rectangle struct. Here we've defined a struct and named it rectangle. Inside the curly brackets we define the fields as width and height, both of which have type U32. Then in main we created a particular instance of rectangle that has a width of 30 and a height of 50. Our area function is now defined with one parameter, which we've named rectangle, whose type is an immutable borrow of a struct rectangle instance. As mentioned in Chapter 4, we want to borrow the struct rather than take ownership of it. This way, main retains its ownership and can continue to use rectangle 1, which is the reason why, which is the reason we use the AND in the function signature and where we call the function. The area function access with width and height fields of the rectangle instance. Our function signature for area now says exactly what we mean. Calculate the area of rectangle using the width and the height fields. This conveys that the width and height are related to each other, and it gives descriptive names to the values rather than using the tuple index of 0 and 1. This is a win for clarity. Adding useful functionality with derived traits. It'd be nice to be able to print an instance of rectangle while we're debugging our program to see the values for all the fields. Listing 511 tries using the print line macro as we have used in previous chapters. This won't work, however. Listing 5-11, attempting to print a rectangle instance. When we compile this code, we get an error with this core message. The print line macro can do many kinds of formatting, and by default the curly brackets tell print line to use formatting known as display, output intended for direct end user consumption. The primitive types we've seen so far in implement display by default because there's only one way you'd want to show a 1 or any other primitive type to a user. But with structs, the way print line should format the output is less clear because there are more display possibilities. Do you want commas or not? Do you want to print with curly brackets? Should all the fields be shown? Due to this ambiguity, hate that word, Rust doesn't try to guess what we want, and structs don't have to provide implementation of display. If we continue reading the errors, we'll find this helpful. Let's try it. The print line macro call will look like print line colon double quotes rect1 is putting the specifier colon question mark inside the curly brackets tells print line we want to use an output format called debug. The debug trait enables us to print our struct in a way that is useful for developers so that we can see its value while we're debugging the code. Compiling the code with this change, drat, we still get an error. But again, the compiler gives us a helpful note. Rust does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do that, we add the annotation hashtag derived debug just before the struct definition as shown in listing 5-2. Listing 5 dash, oh, that's 5-12, sorry. Listing 5-12, adding the annotation to derive the debug trait and printing the rectangle instance using debug formatting. Now when we run the program, we won't get any errors and we'll see the following output. Nice. It's not the prettiest output, but it shows the values of all the fields for the instance, which would be, which would definitely help during debugging. When we have larger structs, it's useful to have output that's a bit easier to read. In those cases, we can use the instead of in the print line string. When we use the style in the example, the output will look like this. Rust has provided a number of traits for us to use with the derive annotation that can also, can add useful behavior to custom types. Those traits and their behaviors are listed in Appendix C. We cover how to implement these traits with custom behavior as well as how to create your own traits in Chapter 10. Our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely to our rectangle struct. Because it won't work with any other type, let's look at how we can continue to refactor this code by turning the area function into an area method defined on our rectangle type. Now we're on to the last 5.3 method syntax. Methods are similar to functions. They're declared with the function keyword and their name. They can have parameters and return a value. And they contain some code that is run when they're called from somewhere else. However, methods are different from functions in that they're defined within the context of a struct, or an enumeration, or a trait object, which we cover in Chapter 6 and 17 respectively. And their first parameter always self, which represents the instance of the struct and method. Struct, the method is being called on. Defining methods. Let's change the area function that has a rectangle instance as a parameter and instead make the area method define the rectangle struct as shown in listing 5-13. Listing 5-13 defining an area method on the rectangle struct. To define the function within the context of rectangle, we start with an impl implementation block that we move the area function within the impl curly brackets and change the first, and in this case only, parameter to be self in the signature and everywhere within the body. In main, where we call the area function and pass rectangle1 as an argument, we can instead use method syntax to call the area method on our rectangle instance. The method syntax goes after an instance. We add a dot followed by the method name, parentheses, and any arguments. the signature for area, we use the and self instead of the rectangle and rectangle, because Rust knows the type of self is rectangle due to this method's being inside the impl rectangle context. Note that we still need to use the and before self, just as we did in and rectangle. Methods can take ownership of self, borrow self immutability as we've done here, or borrow self mutability just as they can any other parameter. We've chosen and self here for the same reason we used and rectangle. In the function version, we don't want to take ownership, and we just want to read the data in the struct, not write to it. If we wanted to change the instance that we've called the method on this part of what the method does, we'd use and mute self as the first parameter. Having a method that takes ownership of the instance by using just self as the first parameter is rare. This technique is usually used when the method transforms self into something else and you want to prevent the caller from using the original instance after the transformation. The main benefit of using methods instead of functions, in addition to using method syntax and not having to repeat the type of self in every method signature, is organization. We've put all the things we can do with the instance of the type in one impl block rather than making future users of our code search for capabilities of rectangle in various places in the library we provide. Where's the operator? In C and C++, two different operators are used for calling methods. You use dot if you're calling a method on an object directly, and arrow if you're calling the method on a pointer to the object and need to determine the pointer first. In other words, if object is a pointer, object greater than something, and I'm drawing a blank on what those are, is similar to star object dot something. Rust doesn't have an equivalent to arrow operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling method is one of the few places in Rust that has this behavior. How it works: when you call a method with object.something, Rust automatically adds in an and mute or star so object matches the signature of the method. In other words, the following are the same. The first one looks much cleaner. This automatic referencing behavior works because methods have a clear receiver, the type of self given the receiver, and the name of a method. Rust can figure out definitely whether the method is reading and self, mutating and mute self, or consuming self. The fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. Methods with more parameters. Let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return a true if the second rectangle can fit completely within self. Otherwise, it should return false. That is, we want to be able to write the program shown in listing 5-14 once we've defined the can_hold method. Listing 5-14 using the as yet unwritten can_hold method. And the expected output would look something like the following. Because the dimensions of rectangle 2 are smaller than the dimensions of rectangle 1, but rectangle 3 is wider than rectangle 1. We know we want to define a method, so it will be written. No, it will be within the impl rectangle block. The method name will be can_hold, and it will take an immutable borrow of another rectangle as a perimeter. What we can tell, we can tell what what type of perimeter will be by the type of perimeter will be by looking at the code that calls the method rectangle dot can_hold and rectangle 2 passes in and rectangle 2, which is an immutable borrow to rectangle 2, an instance of rectangle. This makes sense because we only need to read rectangle 2 rather than write, which would mean we'd need a mutable borrow. And we want main to retain ownership of rectangle 2 so we can use it again after calling the can_hold method. The return value of can_hold will be a boolean, and the implementation will check whether the width and height of self are both greater than the width and height of the other rectangle respectively. Let's add new can_hold method to the implementation block of listing 5-13 shown in listing 5-15. Listing 5-15 implementing the can_hold method on rectangle that takes another rectangle instance as a perimeter. When we run this code with the main function in listing 5-14, we'll get our desired output. Methods can take multiple perimeters that we add to the signature after the self perimeter, and those perimeters work just like perimeters in functions. Associated functions. Another useful feature of impl blocks is that we're allowed to define functions within impl blocks that don't take self as perimeter. These are called associated functions because they're associated with the struct. They're still functions, not methods, because they don't have an instance of the struct to work with. You've already used a string from associated function. Associated functions are often used for constructors that will review a new instance of a struct. For example, we could provide an associated function that would have one dimension, perimeter, and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. To call this associated function, we use the syntax with the struct name. Is an example. This function is namespaced by the struct. The syntax is used for both associated functions and namespace created by modules. We'll discuss modules in Chapter 7. Multiple impl blocks. Each struct is allowed to have multiple impl blocks. For example, listing 5-15 is equivalent to the code shown in listing 5-16, which has method in its own impl block. Listing 5-16 rewriting. Listing 5-15 using multiple impl blocks. There's no reason to separate these methods into multiple impl blocks here, but this is valid syntax. We'll see in a case in which multiple impl blocks are useful in Chapter 10, where we'll discuss generic types and traits. Summary. Structs let you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of the data connected to each other and name each piece to make your code clear. Methods let you specify the behavior that instances of your structs have. And associated functions let you namespace functionality that is functionality that is particular to your struct without having an instance available. But structs aren't the only way you can create custom types. Let's turn to Rust's enum feature to add another tool to your toolbox. That is the end of Chapter 5. And next we'll be on to Chapter 6. And we have a long way to go. So if you're listening to this, I hope you continue. I know I am. And hopefully together we can make it to the end.